Basically, the way we think of a CWE is it's a common language you can use to discuss security vulnerabilities with anyone in your team. We're talking about developers, software managers, security people, high-level managers. It's a way to kind of communicate issues in your code without people having to understand what your code is or what it does. We also use this as a standard way to kind of measure risk in an application. So if you were to say have thousands and thousands and thousands and thousands of CWEs in your code, maybe you have a problem. If you have no CWEs in your code, maybe you should find another static analysis tool. But it's a good way to kind of understand what could potentially be going on in your code. Now, it's very important for us to kind of determine the difference between something existing in code and something that may exist in code. And this is when we talk about the difference between prevention and mitigation. So this specific presentation, we're going to talk about static analysis and how that maps to CWEs. But we can't necessarily say that we can purely prevent all CWEs by using certain tools. We sometimes say we can only mitigate them. Now the difference between this is, if anyone has done formal methods before, this is the difference between sound and unsound analysis. So sound analysis means we can fully find every location where a specific vulnerability might exist. 100% guarantee we can do that. This would be a situation where we can prevent something completely. So let's say in our code we don't use pointers at all. We have successfully prevented any pointer-related errors because we didn't use pointers. Now, most static analysis tools are going to do mitigation. This is when we say we're going to do our best effort to find things, but we can't necessarily guarantee full prevention. Usually mitigation is good enough. We're also going to talk about the difference between application-specific and universal vulnerabilities. Before, we talked a little bit about SQL injection. Can anyone guess which one that would be? Application or universal? I heard application, that is correct. The reason that's application-specific is how many of you have an SQL database in your code? Correct, none of you do. So for you, that CWE doesn't make any sense. We don't care about that. However, we do care about something like a buffer overflow. That would be considered a universal thing. So we care, from our perspective, about universal things. Application things are something else you need to search for. You need to understand your application and do some analysis on that level. But from the language perspective, we need to guarantee, or we need to at least be able to mitigate potential universal errors. So before I said it's kind of hard to prevent certain types of issues, but just by using Ada, we actually prevent a lot of problems. Who here uses Ada in their projects? Who here uses C and C++? No. The reason I ask is C and C++ actually have some vulnerabilities that Ada does not. Let's actually look at what they are. These are kind of interesting. So this is the CWE website. Use of size of on a pointer type. Now, let's say we want to take the size of an array in C, but we take the size of the pointer. What do we get? We get the size of the pointer, not the size of the array, right? Can we do this in Ada? Answer is yes, you can. But it's much harder. The size of isn't a thing. So in Ada, if you take the tick size of an access type, you will get the size of the access type. If you take tick size of an array, you get the size of the array. Which one makes more sense? Tick size of the array, right? So these are the kinds of things that Ada tries to prevent by giving you a better syntactical language to describe your code. As you can see, there's some here that are specific to Java, some specific to .NET. Who here uses .NET? Good answers. And some only affect struts, Java. These are things like that. Now, what's interesting is when we start talking about vulnerabilities that are not specific to the language, but are still prevented by Ada. So for instance, unsafe pointer usage. This is an instance where, let's actually look at the CWE. So this would be casting pointers to various types. This is like using a void star. If you use a void star in C and you cast it to something that doesn't quite map, and then you try to access child numbers of that pointer. This is super dangerous in C. And a lot of times you have to use void stars. What do you do in Ada? You just pass the type. Pass by reference is a wonderful thing. So these are things that you don't necessarily, you can get around in Ada by not doing things that are considered unsafe. Unvalidated code and dynamic eval. This would be running processes from your code. There's a way to do this in Ada using libraries. Confusion between assignment and comparison. Who here has done that before? So in Ada, how do we get around that? Assignment is colon equals, comparison is 1 equals. So we don't have to go, is it 2 equals, is it 1 equals? I can't see that far. Improper null termination of strings, I've done that before. In Ada, we don't have this problem. So we talked about prevention, but these are all things, yeah, we know this. We use Ada for these reasons. Okay, that's fine. So let's talk about what is actually potentially in your code and how we can find these things. So in Ada, we have compiler-generated checks, right? So anytime we try to store a value inside of a type, what happens? That value gets checked to make sure it's within the valid range of that type. Let's say we go to add a number to an integer. What happens? Well, there's a check to make sure that that integer doesn't overflow or underflow. All of these checks contribute to the potential mitigation of potential issues in your code. Now, this is kind of the list that we say just those runtime checks can help you mitigate these things. So here's a big one, buffer overflow. Anything with a star here is in CWE top 25. These are the ones that are the top 25 most common software occurrences or vulnerability occurrences in software. So as you can see, buffer overflows on there. Incorrect calculation of a buffer size. This would be trying to malloc a buffer that's incorrect and you blow over the end. Integer overflow or wraparound. These are the 3 in the top 25. And then all the rest of these are kind of important. 457 or 476 is a null pointer dereference. That one's kind of a problem. It's going back to the void star issue we saw earlier. Numeric truncation, that's a big one. What happens if we convert a float to an int? In C, we don't really know. What happens if we do it in Ada? It's a compiler error. You should have to explicitly do something. So these are all things that the compiler is going to insert text for you. That's fine, but how many do you compile with the checks turned off? A lot of people, right? If you have a small processor, you can't have the extra overhead of the checks, right? So we actually want something that can be able to check these. And I actually realized I had examples of these issues here. So let's come back to that. Let's look at a potential buffer copy without checking the size. This is CWE 120. This is a classic buffer overflow. Can anyone see what I did wrong here in the C code? I'll give you a hint. So we're passing this array into this function that takes a pointer and a length, right? So I have an array here, I'm setting some values, and then I'm passing this into the function. What did I do wrong right here? I passed the wrong size. What happens when I do this? Buffer overflow, right? And how would this be caught? Peer review, right? Some testing maybe? So let's look at Ada. I did the same thing here. Well, do we have a buffer overflow here? No, because I don't have to pass this by pointer and length. I just pass the type. But let's say I actually did something equivalent. And I'm pointing the array and the length, and I try to loop over the length here, which again, this is very wrong. We can do tick range. That makes way more sense. What happens right here when I do overflow this buffer? Buffer overflow, constraint error, correct. So let's look at another one, integer overflow or wraparound. What do I do wrong here? I'll give you a hint, I just said the name of it. Say again?
Condition is not changed.
Right, so we're just going to keep adding to this integer, and eventually it's going to overflow. What happens in C when we overflow an integer?
Nothing.
Oh, I heard wraparound, I heard nothing. Any others? Anyone who says, I don't know, is correct, because it's actually hardware and compiler dependent. It's completely undefined behavior. What happens if we were to do this in Ada? Right, so but let's say we have an integer type like right here in the code. What happens if we add one to integer tick last? Strain error, correct. So again, let's say we want to turn those checks off. And we don't potentially find this in code. We don't potentially find something in testing. Now what do? Well, this is where static analysis comes in. So let's say we want to run some static analysis on this piece of code here. This is the one we saw earlier where we did the buffer overflow. So we're expecting our static analysis tool to kind of find something right in here, right? This length equals 30 is incorrect, and this is a buffer overflow. So if I were to run CodePeer on this, I get this finding. This might be a little small. Anyone can read this. It says buffer overflow. It's a precondition array index check, CWE 120, which is buffer overflow. Failure on call to our procedure requires length equals 0 or length is less than or equal to array tick last. Does that make sense to everyone about that finding? That pretty much tells us what's happening, right? Tells us this is a buffer overflow, you should probably fix this. Do the same thing with our integer overflow problem. So again, we turn checks off. What will happen if we wrap this around with checks off? Undefined behavior, checks are turned off. So we do want to be able to run static analysis here. We want to be able to catch this. So if we run static analysis, we get overflow check, CWE 190. Might fail, requires that the counter is less than or equal to integer tick last minus 1. Does that make sense to everyone? Now, what's interesting about this is I put mitigation here, I didn't put prevention. Why do you think I put mitigation instead of prevention? The reason for that is with Ada, the full Ada language, we are still using constructs of the language that can be difficult to properly do static analysis. This is why anyone who's familiar with Spark exists. So Spark is a subset of Ada where we're able to do proofs that can actually prevent certain things. Instead of mitigation, can prevent. We're going to talk about that in a little bit. But let's look at what we can actually mitigate with CodePeer. The list we see on the left is the list we saw earlier. These are all things that are mitigated, can be mitigated by the Ada language. Now, what CodePeer does is it uses all the checks inserted by the compiler and uses those to actually do its analysis. So it says, okay, any of those raise exceptions that were put in by the compiler, can I hit those? How do I hit those? And how do I figure out what's going on? It can also check for more things. So we have everything that we were checking with Ada. Now we can also check all these things. If you notice here, most of this is race condition stuff. There's a lot of threading things here. So if anyone does use tasking, CodePeer is kind of great to be able to figure out if you do have a potential race condition. What it actually does there is it looks at any critical sections that are shared between tasks and if they're being used outside of a protected object. So with that, it can look for concurrent executions. That's a classic race condition. Missing synchronization or incorrect synchronization. The other things it looks for are kind of more logic errors, which is kind of something that's interesting. So CodePeer can actually back out logic errors. So let's say you have a if statement, and CodePeer can determine that the if statement will never evaluate one of one of the ways. So, let's say it always evaluates it true and never evaluates false. So CodePeer, that's a logic error. That seems like it's why do you have the if statement there. So what CodePeer is going to do is it's going to tell you that the expression is always true. Equivalent example would be, let's say you have a loop, and the loop exit condition can never be reached. Meaning there's some expression in the loop exit, and that loop expression can never evaluate to true. CodePeer is going to say, loop with unreachable exit. Now, most of you probably have at least one loop that doesn't have an exit condition. That's usually your main loop. So there is a way to tell CodePeer that, hey, that's on purpose. Now, this would be the kind of an application thing, right? Instead of CodePeer is telling you global problems. And now you're saying, okay, my application requires this. That's perfectly fine. That's how we kind of make a distinction between global problems and application problems. One thing we didn't talk about yet is the use of uninitialized variables. Who here's had that problem before? Garbage and a variable. So this is an issue. If we have a variable and we just start using it, there's going to be garbage in there. So let's look at this case, where I did some refactoring and I commented out my init global sequence, which is supposed to init all my globals. In this case, it's just one global. I'm lazy. So what happens here? If we were to do this line right here, what do we expect in the put line? Good? Don't know. We have no idea. So what would CodePeer say? Validity check, CWE 457, which is an uninitialized variable. Global is uninitialized here. So this is kind of nice, because if you've ever had this problem, it's really hard to track down. So now CodePeer can help you out here. In this code, how many violations do you think CodePeer will find? The correct answer is run CodePeer and you'll find out. Okay, so let's see what we get. So this loop has an unreachable exit. Why does it have an unreachable exit? Well, we set flag here, and then we check if flag, and then we never change flag anywhere. So CodePeer said, hey, look, yeah, this is, we can never get to the exit. CodePeer is saying this test is always false. Makes sense, because we never change flag. We have some dead code here, because that put line will never execute. Again, same problem. We have a validity check here. This counter will overflow. So that's, counter isn't initialized. That's CWE 457. We have, now we have the overflow. So this counter will overflow. So we have CWE 190. So as you can see, all this stuff's maps to CWEs. So we can actually take this report on this code and say to a security person, here are my problems, here what shows up. Now you know approximately what risk we have. So that's kind of why CodePeer is going to help you out a little bit to determine what potential issues are in your code. Now, from your perspective, it could be, yeah, of course flag's never going to evaluate to true. We never want it to. Perfectly fine. You can justify that. You can say this is a low risk, this is on purpose, whatever. But potentially that counter overflowing could potentially be a security vulnerability. Now we mentioned before about doing CodePeer on Ada, and then having the ability to subset the Ada language a little bit, and being able to do more accurate analysis. This is what's called using Spark. So who here has used Spark before or heard of Spark before? The idea is we use a subset of the language that is more fit for static analysis. Our static analysis tool can use the constructs in the language to give you much better analysis. Now with Ada, you're already doing well. As you can see, the list is pretty good. But if we want to go one step farther, we want to bring in a little bit more safety. We can take certain sections of our code and do them in Spark. Now, what's interesting about that is most people would think, hey, we have to do everything in Spark or nothing in Spark. Well, that's not true. Since Spark is Ada, there's no different compiler. It's all the same. So Spark is valid AdaCore. So let's say you have this one little section that's super critical. You really want to guarantee certain properties of that. You can take that little bit of code, run the Spark prover against it to kind of see how many violations you have, how far outside of the Spark subset you are, which I have a guess you won't be very far outside of that subset. And then you can start doing some Spark proofs on that, which is just a fancy way of saying advanced static analysis. Now you can start to guarantee certain properties of that code. And that gets kind of interesting, because now you can analyze your whole code base with CodePeer. You can analyze small sections with Spark. And you have this ability to now get a good picture of what's going on in your code. You can also restrict the subset, or restrict the features of the language that you're using. If anyone's used pragma restriction before, if you're using Ravenscar runtime, that actually is a pragma restriction. So if we, let's say, don't use allocators, we already prevents everything that's potentially wrong with allocators. So we allocate some memory, we don't free it. We allocate too much memory, we allocate too little memory, we blow over the end of the buffer, things like that. If we remove tasking, we get rid of all of our tasking problems. We talked before about synchronization problems. If we remove recursion, probably a good idea. We lose the ability, we don't have the problem of stack smashing on recursion, infinite recursions. No unchecked conversions, that's a big one. Who here has had problems with unchecked conversions before? That one's a good one to put in, because inevitably someone's going to convert something from one type to another type and they're not compatible. There's a reason we called it unchecked. It's very important. So, moral of the story is, if you want to reduce the risk in your code, first of all, use Ada. Second, use CodePeer. Do some analysis. Third, and if you can go this far, it's very beneficial, move a little bit of your code to Spark and see what happens. You'll see that your QA will go much faster, and the accuracy of that static analysis will be much better. You'll spend a lot less time trying to track down problems with Spark. And as Ben mentioned earlier, Spark and CodePeer are CWE MITRE recognized tools. So if you go on the MITRE website, you go to the recognized tools section, you will see that these two are listed there. Any questions?